Hello, good morning, students. So let us begin with our today's session. So yesterday we started with interrupts, 8051 interrupts, right? So total there are 5 interrupts, 2 hardware, int0, int1, active low. So int0 bar, int1 bar, and 3 internally generated interrupts, timer 0 interrupt, timer 1 interrupt, and serial communication interrupt, right? All the interrupts are vectored and they have a priority. The purpose of having interrupts is so that microcontroller can perform multitasking. Okay, and then we looked into what all operations happen internally inside microcontroller when an interrupt arrives. So we gave an example. Suppose while executing ADD instruction at location 100, int1 hardware interrupt arrives. So microcontroller will first save the return address on stack, jump to the vector address of int1, disable all the interrupts, execute the interrupt subroutine, and iReturn instruction will enable all the interrupts and pop the return address from stack into program counter. And that's how it returns back to the main program. So these are the operations happening internally inside the microcontroller when an interrupt arrives. Okay, and then we looked into what are the vector addresses of all these interrupts. So int0, the vector address is 003. Timer 0, it is 00B. Int1, the vector address is 13 hex. Timer 1, 1B hex. And serial communication 23 hex. So the sequence is int0, timer 0, int1, timer 1, and serial communication. And accordingly, the addresses are 3B, 131B hex and 23 hex. So these are the vector addresses. That means whenever that respective interrupt arrives, these addresses get automatically loaded into program counter. Correct? Mean whenever these interrupts arrive, microcontroller will start executing the program which is written at these addresses 3B, 131B and 23 hex. Is that okay? And whether that interrupt has arrived or not, the programmer can get the indication on the respective flags. Int0, the flag is interrupt enable 0. Timer 0, the flag is timer flag 0. Int1, interrupt enable 1. Timer 1, TF1 flag. And serial communication, RI interrupt and TI interrupt. So these are the flag bits where the programmer can understand the respective interrupt has arrived. Okay, now where are these flag bits available? Hardware interrupts int0, int1 and timer 0, timer 1. These 4 flags are available in TCON register. Okay, TCON.1, 1357. So odd numbers. In TCON register at odd number positions, you get these flags. Hardware interrupt and timer 0, timer 1 interrupt flags. And serial communication interrupt arrival is available in SCON register. SCON bit 0, bit 1. Is that okay? So these flags give an indication. Whenever these flags are set, it means that corresponding interrupt has occurred, right? And it is available in TCON register and SCON register. Fine. And the priority is int0, timer 0. Int0 has the highest priority and the sequence follows int0, timer 0, int1, timer 1 and serial communication. So serial communication has the lowest priority. Now as we said in yesterday's lecture, see the difference in the vector addresses is hardly 8 memory locations. Correct? So it might not be possible whatever program should be executed when that interrupt arrives. It means interrupt subroutine program cannot fit in these 8 memory locations. Then what modification, how do we manage with this, right? So we looked into whenever microcontroller jumps to the corresponding interrupt vector address, at that particular address location, we write another jump either we write jump instruction or we write call instruction, right? So we write another jump instruction at those vector addresses. Okay, so no doubt when microcontroller jumps to the vector address, it will first disable all the interrupts, and programmer will be writing one jump instruction, jump to actual position where the subroutine is written, ISR is written. And then to that label, we write the actual ISR. We do this modification because the vector addresses, the gap between the two interrupt vector addresses is very small, and the interrupt subroutine cannot fit within that 8 memory locations. So that's how the modification is done. Is that okay? So when we will do our today's LED blinking program, we will do it in this way, right? So the next, okay, so then we saw those flag bits int0, int1 and timer 0, timer 1. Those flag bits are available in TCON register. The odd number bits, TF1 is 7, TF0 is 5th, next is IE1, and then other one is IE0. So that is bit 1, bit 3, bit 5 and bit 7. These are the positions where you get to know whether the corresponding interrupts have arrived or not. Okay, and the lower 4 bits are used for hardware interrupts, right? So TCON register lower 4 bits are associated with hardware interrupts, int0, int1. IE0 and IE1 are the flag indicators. If these are 1, it means the hardware interrupts have arrived. Whereas IT0, IT1 decide the active low triggering signal for hardware interrupts, whether it should be falling edge triggered or whether it should be a low level triggered. That is decided by IT0, IT1, interrupt trigger bits. If IT bit is set, it means interrupts are activated by a falling edge signal. And if the IT bit is 0, mean the interrupts are activated by a logic 0 signal, low level signal, right? So whenever you're dealing with hardware interrupts, you should use TCON register also. But if you're using serial interrupt, you need not use TCON. Is that fine? Mean there are flag bits TF0, TF1, but for serial communication, you need not use TCON register. Okay, and now we will be looking into what are the special function registers associated with interrupts. See, one special function register is TCON, correct? But then TCON is for timer as well as for interrupt. But the dedicated special function registers for interrupts are IP and IE. Interrupt priority register, which is used for changing the priorities. It is bit as well as byte accessible. And IE, interrupt enable register, to enable or disable the interrupts. This is also bit as well as byte addressable. The addresses are B8 and A8 respectively. Okay, and I told you all, as we power on microcontroller or whenever we reset microcontroller, all the interrupts are disabled. Programmer needs to write interrupt enable control word to enable the interrupts and then only use it. Okay, so interrupt enable register is what we will see. So whenever we reset controller, the interrupts are in disabled mode, right? We need to write interrupt enable control word. So see here, that blue color, that interrupt enable 8-bit register, right? You can set and clear bit by bit as well as it is byte accessible. Addresses, SFR addresses, A8 hex. So look into the lower bit, EX0. This is enable int 0 bit. ET0, enable timer 0 interrupt. EX1, enable external interrupt 1. ET1, enable timer 1 interrupt. ES, enable serial communication interrupt. And EA is enable all. So this is the control word, interrupt enable control word register. Now from the name itself, it is used to enable and disable the interrupts. If you set the particular bit, it means the corresponding interrupt is enabled. Correct? So if look into that table which is written down, EX0, look at the last row in the table. If EX0 bit is set, it means external hardware int0 interrupt is enabled. If the bit is 0 mean you have disabled the corresponding interrupt. EX1, that is external interrupt 1. EX1 is set mean external interrupt 1 is enabled. ET0 bit is set means timer 0 interrupt is enabled. So whenever the respective bit is 1, it means you have enabled the respective interrupt. Correct? You can enable all the interrupts at a time. It is not a problem. Why? Because if all the interrupts are enabled and if they arrive simultaneously on the priority basis, one of the interrupt will be selected. So whichever interrupts you want, you can enable it using IE register, and this is to be done compulsory. Fine. And look at the last bit, EA. This is a master control bit. Unless and until you don't activate EA, mean you should set EA bit, then and then only whether the lower bits, whether it's logic 0 or logic 1, will be considered. If EA bit is 0, mean it's a master disable. If EA bit is 0, whatever logic 1, logic 0 you have entered on EX0, ET0, EX1, ET1, ES will be ignored. Correct? So whether the interrupts are to be enabled or disabled, that depends on the master control bit. That EA bit should be set. Are you getting me? So EA bit is 1 is, it is allowing to enable the interrupts. If EA bit is 0 mean all the interrupts are disabled. And along with EA bit, you need to set or clear the respective interrupts. The one that you want and the one that you want to disable. Okay, so that is compulsory. You need to write IE register whenever you are using interrupts. Fine. And the next interrupt priority register. So look into this is an 8-bit interrupt priority register. Address is B8 hex. It is bit as well as byte accessible. Look into those lower bits at the register. PX0, that is priority for external int0 interrupt. PT0, priority for timer 0 interrupt. PX1, priority for external int1 interrupt. PT1, priority for timer 1 interrupt. And PS, priority for the serial communication interrupt. Whatever bit you set, it means that will act as a highest priority. Okay, so whenever you set the respective bit, that interrupt will have an highest priority. So for example, see here, by default, who has the highest priority? Int0. So what is the default priority status? Int0, then timer 0, int1, then timer 1, and serial communication has the last priority, lowest. So with the help of IP register, what I can do is I can enable all the interrupts and I can make serial communication the highest priority. Correct? So how will I write the control word? PS. At the PS bit, I will set the PS bit, whereas the remaining bits I will make 0, 0, 0, 0. So if in IP register, if the PS bit is set, it means serial communication has the highest priority now. And the remaining interrupts will follow the default priority. What was the default priority? Int0, highest, then timer 0, int1, timer 1. Mean whatever the remaining interrupts are, how will the new priority be assigned? If the PS bit is set, then the first priority is to serial communication. Correct? And the remaining interrupts will have the default priority. So what is a priority sequence? See here students, PS is the first priority, int 0 second, timer 0 third, int 1 fourth, and timer 1 fifth. That's how the priority will be reassigned. Are you getting me? Right? If that PS bit was set, I repeat again, if that PS bit was set, it means serial communication will get the first priority, highest, and the remaining interrupts will follow the default priority. And what was the default priority sequence? First int 0, timer 0, int 1, timer 1. So the new sequence, priority sequence is PS is 1, first priority, int 0 second, timer 0 third, int 1 fourth, and timer 1 fifth. Fine. So if the respective bit is set, that particular will get the first priority, highest. Now, what if you set more than one? So for example, PS is set, serial communication priority is set, and as well as timer 1 priority is set. I hope you are understanding what I meant to say. Just let me show it to you. What am I saying? Let me show it to you. So for example, I was telling, if I am setting the PS1 bit as well as if I am setting the timer 1 bit, whereas the other bits are 0. This is 0. Okay, this is 0, and suppose this is 0. Hope I have shared. If I write the control word something like this, set the serial priority as well as set the timer 1 priority. So I have set two priorities, and the other priority let them remain as by default. Then what will happen? Microcontroller will look into how should we resolve this. This priority is resolved depending on what was the default. If you compare serial and if you compare timer 1, who was having the highest priority? Timer 1. So what will microcontroller do? The first priority is given to timer 1. Second priority is given to serial communication. And the remaining will follow the default. Out of the remaining, who has the highest? Int 0, timer 0, and then it will be int 1. So the new priority status will be timer 1 first, serial communication second, int 0 third, timer 0 fourth, and int 1 fifth. So just mean how will the new priority be resolved? See, if I wish to show it here. So the priority for timer 1, the priority for timer 1 is 1, serial communication is second, int 0 is 3, timer 0 is 4, and timer 1 is 5. So that's how will be the new priority structure. If you are setting the priority for multiple interrupts, that's how it is resolved. So now with this, let us go to one of the programs. So now we will look into one interrupt program for using timer 0 interrupt. Okay, so let us do one LED blink program using timer 0 interrupt. Let us read the problem statement. Write a program to blink an LED connected to P1.7 of microcontroller at a rate of 0.265 milliseconds using timer 0 interrupt. Okay, so we will do LED blinking using timer 0 interrupt. And what is the rate at which LED blinks? The LED blinking should be at a rate of 0.265 milliseconds. We are using timers as well as we are using interrupts. So for writing the algorithm, right, we will just note down what all steps do we need to follow to do this LED blinking program. So the first step, since I am going to blink the LED at a rate of 0.265 milliseconds, so I will use timer 0 to generate a delay of 0.265 milliseconds. And whenever 0.265 milliseconds are completed, that delay is completed, an interrupt will be generated. And whenever an interrupt will be generated, the LED will be either turned on or turned off. Is that okay? So let us first go for initializing the timers and then let us go for initializing the interrupts. So the first thing that we need to do with timer is to generate a delay of 0.265 milliseconds. What will be the count calculations? So if you remember, for 12 megahertz F oscillator, that is the oscillator frequency, if I use timer 0, right, in mode 2, correct? Why am I using mode 2? Because every time I need this 0.265 milliseconds delay. So I need this delay continuous all the time. So let me initialize timer in auto reload mode, and that auto reload mode is mode 2. And if the oscillator frequency is 12 megahertz, mode 2 is an 8-bit counter. I get a delay of, if I use the full 8-bit count, I get a delay of 0.265 milliseconds. So I just show that to you. So see here students, whenever we were studying timers, so if I keep timer 0 in mode 2, then it is an 8-bit timer counter, right? So 8-bit timer mean I'll be getting 256 counts. So if the oscillator frequency is 12 megahertz, then the frequency arriving at the timer is 1 megahertz. So at 1 megahertz internal clock, if I use the entire 8-bit count 00 to FF, we will be getting a delay of 0.256 milliseconds. Okay, so that should be, I need to change that. Okay, I'll make it 0.256 milliseconds. So I will use mode 2 auto reload. Okay, so this should be 0.256 milliseconds. So let me make it 0.256 milliseconds. So as we saw, if I keep timer in mode 2 and for 12 megahertz F oscillator, I will get a maximum delay of 0.256 milliseconds. So then what is the count that I should be loading? The count that is to be loaded in TH1 register will be 00 hex. Is that okay? So 00, 01, 02 and so on. As it goes to FF, we will get 256 pulses counted, and hence we will get a delay of 0.256 millisecond. So this is the first thing to do in timer initialization. So timer 0 in mode 2 and the count loaded for 0.256 millisecond is 00 hex. Okay. So then the next we will initialize the TMOD register. So TMOD register, what had we thought of? Timer 0 in mode 2, correct? So the control word comes as, I am using timer 0, not the upper timer. So the upper 4 bits are 0, 0, 0, 0, and the lower 4 bits, the software enable, that is the gate bit is 0. We are using that peripheral as a timer peripheral, and it's mode 2. Mode 2 is 1, 0. So the control word comes as 2 hex. So that's the control word for TMOD register, right? And now before starting the timer, what do we need to do? We need to initialize the timer interrupt. How are we going to work this out? Whenever 0.25 millisecond delay is over, timer 0 will generate timer 0 interrupt. So let us enable the timer interrupt. Enabling the timer interrupt mean I need interrupt enable register. And how is that interrupt enable register? We saw just now. Interrupt enable register, I need to enable all the interrupts first so that MSB bit is set, right? Then the other 2 bits are don't care. The next, I don't need serial communication, right? And then what are the lower 4 bits? The lower 4 bits, the LSB bit is for enabling int 0 interrupt. Then the second bit is for enabling timer 0 interrupt, and I need that. So let us enable timer 0 interrupt, right? Next, I don't want int 1 interrupt and I don't want timer 1 interrupt. So see here, what is the control word that will enable only timer interrupt? That is 82 hex. Interrupt enable register. Here I'm showing here interrupt enable register. Which interrupt I need to enable? timer 0, so that the second bit should be set and the master enable bit should be set. So the control word is 1 0 0 0 0 0 1 0. So the control word comes as 82 hex. 82 hex. Now we have enabled, we have initialized the timers, we have loaded the count, we have enabled the interrupts. We need to start the timer 0. How do you do that? By setting that run bit. So SET set bit which TR0. Start the timer. So this will be our main program. Is that okay? So this will be our, all the initializations will be our main program. Now let us write the ISR, interrupt service routine. What is to be done in ISR? Okay, what is to be done in ISR? We should be blinking that LED. Mean for initially, if I assume LED was on, after 0.25 milliseconds, I will turn off the LED. After another 0.25 milliseconds, I will turn on the LED. Again, after this much time, off, on, off, on, off. This on-off rate is of 0.25 milliseconds. So what is to be done on arrival of the interrupt? Change the LED status. If it is on, make it off, or if it is off, make it on. So it means, what do I need to do? Change the LED status. Right? It means what how will I do this? If it is on, I need to turn it off, or it is off, I need to turn it on. It means I should complement that LED. Where is that LED connected? To P1.7. It means I should be complementing P1.7 bit. This is the instruction that I will use. So on arrival of the interrupt, I need to blink that LED. If it is on, let us make it off. So the interrupt service routine is just changing the LED status, right? And then I return, right? We will be returning to the subroutine. And which interrupt we are using? That ISR is for timer 0 interrupt. Timer 0 interrupt, what is the vector address? That vector address is 000B hex. Do you get me, students? So we are going to do LED blinking at a rate of 0.256 milliseconds, and this 2.256 millisecond rate will be obtained by timer 0 interrupt. Let us write the program for this. Program, turn on and off the LED at a rate of 0.25 milliseconds. So let us start with the main program. So main program begins with org 00 000 hex, and then we write sjump next, and okay, and then we start with the label next, right? Now see, it's an interrupt, right? Whenever an interrupt arrives, microcontroller is going to stop the current execution and it is going to jump to interrupt service routine. While jumping to interrupt service routine, the return address is going to be saved on stack. So it means whenever microcontroller is dealing with interrupts, stack is used to store the return address. So in main program, the first instruction should be initializing the stack pointer. So let us do that. So mov sp comma hash 50 hex. So let us assume the stack memory should begin from memory location 50 hex onwards. And let us do those initializations as we just saw it now. What is it? To achieve a delay of 256 millisecond, the count that is to be loaded in TH1 register is 00 hex. So MOV TH0, yeah, we are using timer 0. So MOV TH0 hash 00 is the count that is to be loaded in the higher register. Then initialize the tmod control word. So MOV tmod and the control word timer 0 mode 2. That control word came as 02 hex. So timers have been initialized. Now enable the interrupt. So MOV IE comma hash, that enabling timer 0 interrupt, the control word came as 82 hex. Okay, and then we start the timer. So that is set bit. Which bit? The run bit of timer 0. Is that okay? And now we need not keep on checking the flag, students. We are not doing polling. What are we doing? We are dealing with interrupts. So we will turn on the timer and we will wait in this loop. So we will write an instruction sjump here. And where is the label here? To the same instruction. Is that fine? Okay. And now whenever that 0.25 millisecond is over, TF0 flag will be set, and this TF0 flag will act as an interrupt. Right? Microcontroller need not keep on checking the TF0 flag with the help of instruction. Fine. Now, when an interrupt arrives, right, to which vector address it is going to jump? It is timer 0. Is that okay? Automatically it is going to jump to that vector address. So ISR, what should be done in ISR? Right? What should be done in ISR? Just change the status of that LED. Now that is only one instruction. So let me write, as soon as it jumps to that address 000B, what is to be done? So let me write org 000B hex, right? What is to be done? Complement. Let me write the instruction there itself. Complement P1.7. Is that okay? And then then we return RETI. That is the only thing to be done. Is that okay? So complement that bit and return to the main program. Right? Now in main program, see, we have kept timer 0 in auto reload mode. Mean the count will be loaded again and again automatically. We need not stop the timer. Right? And as a microcontroller jumps to the ISR, interrupt service routine. Okay. What have we written here? ISR. ISR. So as soon as microcontroller jumps to the interrupt subroutine, the timer 0 flag will be cleared. So again, we need not clear the timer 0 flag. When microcontroller is executing any of the interrupt, right? Timer 0, timer 1 flags are automatically cleared. Whereas serial flag, serial communication, RI and TI, the programmer needs to clear these flags. Right? Receiver interrupt and transmission interrupt flags are cleared by the programmer, but the timer flags are cleared by microcontroller itself only when the interrupt service routine is getting executed. Is that okay? So now that is the program. Let us execute this program and see. Okay, see, so whatever program we had seen on that slide, the same program I have already written here. So let me save it, right? The program that we have written, org00, and then we sjump to the label next, and from label next, the first instruction is initialize the stack pointer to 50 hex, then load the count in TH0 register, the count 00. Then initialize the TMOD register 02 hex, mode 2 auto reload. Then enable timer 0 interrupt, MOV IE hash 82 hex, and then we start the timer. So that count up begins. Right? And then we waited in an unconditional loop, never ending unconditional loop. So that was our main program. And after 0.256 milliseconds are over, timer interrupt will be generated. Automatically, microcontroller will jump to an address 000B hex. And what are we doing at that vector address? We are complementing that P1.7. That is, we are LED, whether it is on or off, we are changing the status of LED. And then we return to the main program. Okay. So that's the program we had discussed. Now let us save it, save the program. Let us check for syntax errors. Yeah, missing end statement. So let me give END assembler directive. Okay, so let us build the target. 0 error, 0 warning. Correct. Let us go for executing the program. Now during execution, right, I will activate that interrupt peripheral window. Correct. Next, LED blinking is at P1.7. So let me take IO port 1 at P1.7. That is the last MSB bit. It will keep on blinking, right? And even I have used timers. So let me choose timer peripheral, timer 0 peripheral. Okay. So this is timer 0 peripheral. Now see here students, I will put this program into burst execution mode, and then you will see after every 0.25 milliseconds that TF0 flag is set, and when this TF0 flag is set, microcontroller will jump to that ISR and will change that P1.7 bit. After another 0.256 millisecond, that P1.7 bit will keep on changing its state, so that logic 0, logic 1, logic 0, logic 1 will keep on appearing at after a time period of 0.25 milliseconds. So this is with the help of interrupt. So let me run the program and you all observe P1.7. So see here that P1.7 is continuously blinking, tick, untick, tick, untick, right? And this is happening because of the timer 0 interrupt. See students, we have not written checking the TF flag, right? Instead, what have we done? We have initialized the timer 0 interrupt. And whenever that interrupt arrives, that LED is getting complemented. When that interrupt arrives, after every 0.256 milliseconds. That's how we make use of interrupt. Microcontroller is free to do some other operation. It need not keep on checking the flag and checking whether 0.256 millisecond is over or not. We initialize the timer, it keeps on counting up in the background, and when the counting finishes, it interrupts microcontroller. And then microcontroller stops the current execution, executes the ISR. In our case, it blinks the LED and returns back to the main program. Correct? And at the background, again timer will start counting up because we have put it in auto reload mode. Is that okay, students? Now see one more modification in this. Okay, so let me come out of the debug mode. See, the ISR I have written at 00B hex location itself. Instead, what did I say? If the interrupt subroutine is lengthy, your program cannot fit in the vector address location. So generally what do? At that vector address, we write one jump instruction. So I'm writing one short jump instruction, and let me say the label is ISR for timer 0, ISR T0. And at ISR T0, right? At ISR T0, that's the label of the interrupt subroutine. At ISR T0, I'll be writing what is to be done during the interrupt. When the interrupt arrives, complement that P1.7, that is blink the LED. And then we return from that ISR. So this is what we had seen in the explanation, right? That interrupt subroutine is not written at the vector address. What is written at the vector address? Unconditional jump to some label. In our case, ISR T0. And at that label ISR T0, we write the interrupt program, interrupt subroutine. So let us execute this and see whether it works the same as before. So build target, 0 error, 0 warning. Okay, let us go to debug, start debug, and let us run the program and see it's working now. That P1.7 is blinking, right? That P1.7 is blinking. Now again I want to tell you all, this is just software, right? It's not an actual hardware. So you cannot count 0.256 milliseconds exactly, right? The software it will only tell you whatever program you have written, that logic is correct. But exact 0.56 millisecond you will get to measure only when you load this code in hardware, inside that microcontroller hardware. Fine. The software will only tell you the logic is correct. So thank you, students. Thank you for attending, and I'll stop here. See you in the next session. Okay, bye.